Right. Welcome again. Let's continue new chapter 5. Chapter 5 is about the heat transmission in building structures. Okay. Why we need to study the heat transmission in building structure? Basically, this is a foundation for a space heating load calculation that would be in chapter 6, as well as the cooling load calculation that will be studied in chapter 8. So basically, to calculate the space heating load and the cooling load, uh, the heat transmission through the building is a foundation, right? If you look at this figure, for example, this is let's assume this is a building, and the heat may flow from outdoor to indoor or from indoor to outdoor. It depends on the weather condition. The natural flow of the heat is from high temperature to low temperature. Let's assume that if the weather is a summer condition, right, summer season, then outside temperature is higher and the inside is a cooling one. So that means the heat will flow from outside to inside. Now, if the weather changes, let's say during a winter, nowadays inside temperature of the building is higher, whereas outside is lower. So then the heat will transfer from inside to outside. But the heat transfer normally take place in the form of three modes of radiation. I hope you have studied in very details the heat transfer phenomena through conduction, convection, and radiation. And when we say the building structures, there are so many things that are included in the heat transfer through the building structure. For example, the important one, they are like the walls. I mean, this is a wall. Let's say this is a wall. This is a wall. Similarly, the front wall and the back wall, and then the insulation. This is not a common trend in Pakistan, but the countries where the outside the ambient temperature is too low, there the insulation plays an important role. So outside, I mean, one of the layer in the wall is an insulation layer. Similarly, there are insulation layer in the foundation as well, just to minimize the heat transfer from inside to outside. And similarly, the building structure mean the roofs, right? So this is a roof, as well as the ceiling, right? The doors, right? The windows, the concrete floor. I mean, even in the floor, we have many layers. I mean, the top layer normally we call the floor. I mean, the concrete floor. And then behind the concrete floor, we have so many layers. For example, the lowest layer is a soil, right? That's we call the soil, right? And then on the soil we put what we put concrete, right? We normally called RCC, reinforced concrete, right? And then we put grade, I mean we call the grades, right? That's a layer of the grade. And then there is a unfinished concrete, and then we have the final, the flooring. In some cases they also mount some tiling as well. So when I say the floor may have many layers. It depends on the types of the constructions. Similarly, we have the walls below the grade. I mean, if this is the grade, then you know that along the side foundation, let's say this is the floor. Let's say this is the floor area, but you know that the foundation even goes up to very down, up to long depth, right? So that means the heat transmission is also possible through the wall which is below the grades, right? Grade layer will be like here, and below than that, I mean, the foundation wall is possible there. So one of the transmission component is wall below the grade. Even the floor slab, I mean, the floor slab means the rough flooring, right? And then there could be the crawl spaces, or even some pipe could be buried beneath the building, and that pipe may contains, let's say, the steam is flowing. So as a result of that steam, the heat may transfer into the room or into the building. So there could be many sources of the heat transmission from outside to inside or from inside to outside. And now in the next coming slide, we'll see that how can we calculate each component. I mean, for example, how can we calculate the heat transmission because of the wall, because of the insulation, because of the roof, and how can we calculate because of the windows, through doors, or from the buried pipes, right? But basically, whatever is the component of the building structure, the heat transfer will be out of these three modes of heat transfer. You know that that would be the conduction, convection, and radiation. This diagram explains well the difference between. I hope you already familiar and you have studied the heat transfer subject in very detail, as this is the transfer of heat through from one molecule to another molecule. We also call the diffusion, and because of the movement of the fluid we call the convection, and this is the radiation which transfer energy in the form of rays, right, waves, or it is also called or the particle, right, we call it as a radiation. Now let's consider first the heat transfer uh, through a flat wall. So let's say this is a flat wall, right? And it has, let's say, indoor condition and outdoor condition. Let's say this is point 1, and the point 1 has a temperature, let's say T1, and its dimension is, let's say, x1 with reference to any point. And similarly, let's say the outside is, the point name is T2, so the temperature is T2, and the thermal conductivity of the wall is K. So using the heat transfer phenomena through the conduction, because this is a solid wall, so the heat transfer will be by using the phenomena of the conduction. Which law is called? What is the name of this law?
Fourier's law of heat conduction.
Yeah, this is the Fourier's law of heat conduction. So that means the heat transfer through the wall will be calculated by using the Fourier's law of heat conduction. So you are familiar with that. This is basically the temperature difference, and this is the thickness of the wall, and K is the thermal conductivity. The negative sign is the heat transfer is always in the negative gradient, right? And normally, you know that such type of the resistance phenomena, the heat transfer, normally we represent in terms of the thermal resistances, because just like in electricity we have a potential gradient, so because of the potential gradient current can flow. So similarly the heat flow because of the temperature gradient. So if we have a temperature gradient, let's say T2 minus T1 is the temperature gradient, so because of that temperature gradient heat flows, Q dash flows. So that means we can, I mean, analog to electrical system by converting this in the form of the thermal resistance, right? Instead of electrical resistance we do have a thermal resistance, right, which is resistance to heat transfer. So you can see this is a temperature gradient and this is the resistance. So that means the resistance in that case is equal to, I mean, that x2 minus x1, right, into Ka, right? Only the negative sign is the indication of the decrease in the temperature gradient. And likewise for unit area, or it is also called the unit thermal resistance, that is equal to delta X by Ka, right? So in terms of, I mean, per unit area, we may write the unit thermal resistance as delta X by K, right? So we can adopt the same techniques to analyze the other component, like to analyze the wall slab, which is made of more layer. Instead of one layer, I mean, the wall can be consisted of the several layers. Normally, I mean, the outer layer is normally a brick, and then we put cement, and then another the plaster of Paris. So sometimes we also mount some wooden inside that, right? So there even in some extreme condition in cold areas, the insulation is the compulsory part of the wall component. So how to calculate the overall resistance if the wall is a multi-layer component? As you can see here, I mean, in the figure B, you can see, I mean, this is a complete wall, but in that case, wall consists of three layers now. Like K1 is the first layer, thermal conductivity of the first layer, then thermal conductivity of the second layer, then the thermal conductivity of the third layer. Whereas this is the inside temperature and this is the outdoor temperature, and each component has a certain thickness. For example, this is the delta X, delta x1, delta x2, delta x3. So how to calculate in that case the heat transfer through this wall? So in that case, we have to calculate an overall resistance, right? Overall resistance of the complete valve. Since these valves, they are in series, so this is just a sum of all the resistance which are in series. I mean resistance of the component K1, resistance of the component K2 plus resistance of the component K3. So the equivalent resistance or the overall resistance is the sum of R1 plus R2 plus R3. Whereas R1, just like I showed you in the previous slide, that's delta X1 K1A. I mean, the heat transfer area is this one. If this is the direction of the heat transfer, so this is the area which is perpendicular to the direction of the heat flow. So that's the area. So let's say in that this is a plane wall. So in plane wall, the area remains constant. In which case the area is variable. Area is variable. In which case?
In case of circular cross section, that is cylinder.
Yeah, like cylinder. So the area is not constant, right? So in that case, we cannot ignore the area. In that case, I mean, area is a common one. So we may take the resistance per unit area, but if there is a cross-sectional area, I mean the cylindrical cross-sectional area or spherical cross-sectional area that has certain thickness, in that case, we cannot ignore the area. As you can see in this figure, this is the radial heat flow. Let's say in a hollow cylinder, as you can see, let's say this is the thickness of the pipe, and let's say inside the pipe there is a fluid. So let's say it has temperature here is different. Let's assume that whatever is the temperature of the fluid, the same is the temperature of the inner layer of the pipe, and similarly whatever is the ambient temperature, let's say that's the same temperature at the outer layer of the pipe, and let's say it has a thermal conductivity K. So in that case, again, the heat transfer will be because of the temperature gradient. Actually, I'm not driving this. I hope that you have done all this in heat transfer. So that's the temperature difference between the outside and inside of the pipe. And this is the basically, I mean, 2 pi KL divided by ln R naught by R1. So now this component will represent the thermal resistance. I mean, ln R naught by R1 divided by 2 pi KL. So this is the thermal resistance for a cylindrical pipe or for a hollow cylinder. So that means RO is the outer radius, Ri is the inner radius of the pipe, whereas L is the length of the pipe. I mean, there is the cross sectional, it must have certain length of that pipe. So L is basically the length of that pipe, and K is the thermal conductivity of that pipe. Right. So similarly, a pipe can have the multi-layer. As you can see, this is the, I mean, this is the pipe. This is the pipe, but pipe is, I mean, surrounded with a certain insulation. This is an insulated pipe. So that means now it has two thermal conductivity. One thermal conductivity is the thermal conductivity of the pipe. Another one is the thermal conductivity of the insulated material. So similarly here, the heat transfer, let's say from inside to outside, will be computed by using the concept of the thermal resistance. One of the thermal resistance, let's say we start from the pipe, let's say this one. One is the thickness of the pipe. Another one is through the insulation. So the overall resistance will be the sum of these two. Actually, there is a resistance from because of the inside, I mean, because of the flow of the fluid, that resistance we call the convective heat transfer resistance. And similarly, there is the outer resistance as well. I mean, this HO represent the convective heat transfer coefficient from outside because of the T naught. Similarly, HI is the convective heat transfer coefficient inside the pipe. So actually, there are four resistances that are in series. One is, I mean, this is first one is the convective heat transfer resistance. Then we have the conduction, then again conduction, and the fourth one is again convection. So the overall resistance we can calculate by summing up all of the resistance. I mean, 1 by H, I mean, first of all, the outer one, let's say this is the, I mean, you know that the resistance for the convective heat transfer coefficient is H naught A naught, because heat transfer in a convection, let's say Q naught in convection is basically HA delta T. So similarly, the heat transfer because of the temperature gradient. So we can write it as, delta T by R, whereas that R is equal to 1 by HA. So that means the resistance because of the convection is 1 by H naught A naught. And then we have this insulation. So insulation means we have the R3, this is R3, and then we have R2. So ln R3 by R2, 2 pi K to L. And similarly, again, we have the pipe, right? This is the pipe. So again, for the pipe, ln R2 by R1, 2 pi K1, because this is the thermal conductor K1 into L. Plus, again, inside is convective heat transfer resistance, 1 by H1 HI. So this is how we can calculate the equivalent resistance. And these resistance, sometimes it is not easy to calculate the resistance. These values of the resistance, but the coefficient like HO, HI, these are the heat transfer coefficient. Similarly, the properties, thermal conductivity, these are the properties. These can be computed from the experiments. You perform once some experiment and you can have the experimental data. From that experimental data, you can develop some correlation for the heat transfer coefficient and for the thermal conductivity. So the ASHRAE has provided these parameters, these constant, basically you can say, for the different conditions, for different materials. As you can see in table 5-1, there is a range of the building materials. Actually, I have not put all of the table. The 5-1A, that table has 4 pages on your book, McWhiston book, but I have just included just to show you that how the properties are available. In our book, as you can see, this is the building board. So these materials are just the building boards. In building boards, you have so many varieties with different thicknesses. For example, as you can see, this is a board which has a thickness of 0.25. As the thickness is increasing with different range, and even the material is changing. This is the gypsum or plaster board. Then we have the polywood with that thickness, right? Polywood with that thickness similarly. So again, we have some other material as well. So you can see the properties that are available, the density is available for these material, thermal conductivity and conductance is available, CP values are available. Sometimes the conductance is the opposite to the resistance. This is the reciprocal of the resistance. So sometimes you cannot directly calculate the resistance, but you can measure experimentally conductance. So if you have the conductance, that means you can calculate the resistance, right? So you can combine these resistances just like you did in electrical system. As you can see, for example, in that plane wall, as you can see, this is a plane wall. So let's say this is the inside and this is outside, right? So the flow from the inside, let's say we have the winter season. So that means inside, the direction of the heat transfer will be from inside to outside during the winter. So let's the heat transfer. So the outside, the first one heat transfer from inside to the wall is through convection. And then let's say this is the solid wall. So this is the conduction one. And then from the outer wall surface, there are two modes of the heat transfer. One is the convection, another one is the conduction. Now conduction mode of heat transfer is a temperature dependent. Normally the conduction heat transfer mode is more dominant at high temperature. But if the temperature is low, normally we can ignore the heat transfer because of the radiation. But actually, whether it is a small portion, but the radiation due to the heat transfer due to radiation will be there. So now you can see, let's say this is one of the resistance. So let's say this is Ri. The next one is in series. So again, resistance because of the wall. And then from this, we have the two parallel resistance. One is the resistance because of the radiation. Another one is because of the convection. So these two resistances, one because of the radiation and another one because of the convection, they are in parallel. So we can calculate the overall resistance of this plane valve by summing up this. I mean, let's say Ri1 Rw plus, I mean, the equivalent resistance of these two parallel resistances. I mean, let's say what will be the resistance of the equivalent resistance of these two? 1 by R equivalent, let's say 1. That will be 1 by R, 1 by R plus 1 by R naught, right? So once you calculated R equivalent 1, then you can add up all of the three resistance. Then you can calculate the overall resistance. Similarly, we can have an airspace between the two walls. Let's say one of the layer is this much. Basically, the airspace is provided just to create an insulation, right? Because sometimes the insulation material is expensive one. So instead of using some insulation material, you put an airspace between the two layers of the wall. Let's say one layer is this one, and in between the two layers you have created an airspace. So airspace act as an insulation. So that means this is another resistance, right? Air is another resistance to heat transfer, right? So let's say in that case, for example, outside air, let's say outside heat Qi. So we'll have one of the resistance is a convective resistance, let's say Ri, and then I mean this is the Ri, and then because of this one, I mean this is the conduction one, so then we'll have another resistance, the conduction resistance, and then the airspace will have two parallel resistance, one because of the convection, another one because of the radiation, and then we have the solid valve, again conduction, and then we have the convection, right? In that case, they have not included the radiation at the outside surface. That may be because of the temperature effect, but the radiation is always there, right? Normally the air, I mean resistance because of the airspace. I mean R, let's say R air, because this resistance is because of the airspace, and in airspace we have the two parallel resistance, one is the convection and one is the radiation. Now this resistance is experimentally calculated, right, depending upon the thickness of the airspace. So the ASHRAE, through the experimentation, instead you calculate all of the resistance for every case. They have provided the overall resistance because of the airspace for different thicknesses of the airspace. I'll show you the table where you can calculate the thermal resistance because of the airspace. Now, as you can see here, I mean some of the resistance can be parallel, some of the resistance can be series. So you have to calculate the overall resistance. So this is the formula for calculating the overall resistance of the parallel component. As you can see, for example, here you have some of the component in series, whereas some are in parallel. As you can see, wall 1, 2, 3, they are series with each other but parallel with the resistance 4. So how you will calculate the overall resistance of this system? I mean R1, right? R1, R2 and R3, they are in series, right? Let's say this is R1, R2 and then R3. So these three resistances, they are in series, but they are parallel with the resistance 4. So that means we have to put a parallel resistance, let's say R4, right? So we have to calculate an overall resistance for this complete valve, right? So I mean, you know, I hope you know how to calculate. First of all, we'll calculate the equivalent resistance of the R1, R2 and R3, right? Let's say that's R4, right? I mean sum of this. Then the R4 and R, let's say this is R5, let's say R5. Then the R4 and R5, they are in parallel. Then we'll calculate the equivalent resistance of R4 and R5. Right, and how to calculate the I mean the heat transfer because of the radiation. I mean one way is that we calculate the resistance, right? I mean again the radiation, if there is a temperature gradient between the two surfaces, then there will be the radiation transfer from one surface to another surface. Let's say if we have two surfaces, let's say surface 1, right, and the surface 2, right? We have two surfaces, surface 1, surface 2, and let's say this surface has the property, let's say A1 epsilon 1. Similarly, the second surface has the area, let's say A2, and the emissivity is, let's say, epsilon 2. Let's say the temperature on this surface is T1 and temperature on the surface 2 is, let's say, T2. Now, how to calculate the net heat transfer between these two surfaces, right? How to calculate that? We'll use this formula. I hope you have derived this formula in the radiation. Basically, in radiation, there are two types of the resistance. One we call the surface resistance, another one we call the space resistance, right? This one is the surface resistance because of surface 1, right? And this one is the surface resistance because of surface 2. And this is the space resistance between them, and it depends on the shape factor. This is also called view factor. It also called configuration factor. It has three different names: view factor, configuration factor, right, or the shape factor, right? So this is basically the representation of the space resistance, whereas these two terms, they are the representation of the surface resistance. So this is basically the overall resistance of the radiation. So if you have two objects which are at two different temperature, T1 and T2, then the net heat transfer between the surfaces will be equivalent to this temperature gradient divided by the resistance. So this is basically the resistance of the radiation. Sigma is the Stephen-Boltzmann's constant, right? It has some constant value which is equivalent to, in British unit, this one, and in SI unit it has a value of this one, right? And epsilon is the emittance, right? I hope you know this formula because this is a concept that you study in heat transfer. Right. Similarly, for this case, as you can see that I mean, this is the first one. That's the because of the, I mean, outside because of the convection. So first resistance will be because of the convection, which is, let's say, 1 by Hi Ai, right? And similarly, then we have the conduction. So conduction is, let's say, how much is the thickness? Let's say this is delta x1. So let's say delta x1 divided by k1 a1. And then this is the space resistance. So we have the equivalent space resistance that depends on the value of the thickness of the space. And then again, we'll apply the conduction one, and then again the convection. So you can rewrite here. The first one is this one, the convection, and then we have the conduction, and then this R2 is basically the representation of the resistance because of the airspace, and then we have the conduction, and then we have the convection. So you can calculate the overall or the equivalent resistance. All resistances, they are in series now, because in airspace we have represented this with an equivalent resistance, right, through experimentation. And how can we calculate the overall heat transfer? I mean, from outside surface to inside surface, what is the overall heat transfers through that wall, let's say? So we need an overall heat transfer coefficient, right? UA, I mean, the product of UA is, it's called conductance, right? What is the overall heat transfer coefficient? You have to multiply the conductance with the delta T. You can also calculate the heat transfer per degree of the temperature difference. Sometimes the delta T is not given. So in that case, you calculate the heat transfer per degree of the temperature difference. And then in table 5.2, you can see the value of the conductance and the resistance because of the air. I mean, because of the air motion. I mean, let's say if this is the inside of the room, let's say this is the inside of the room. So normally in inside of the room, we use still air, right? So instead of, I mean, using this 1 by HIAI, you can represent as equivalent to resistance, right? So that means if you know that what is the velocity of the air inside of the room, you can directly calculate the value of the resistance. I mean, what is the value of the R, right? Even the value of the H can also be calculated. If you know the value of the area, I mean AI, HI, you can also calculate the resistance, but you can also directly use the value of the R as well, right? Similarly, you can directly use the value of the R as well for different velocities of the air. For example, you can see the still air and the direction of the heat flow is also matters, whether that still air is on a horizontal surface or the vertical surface, because when you will study, let's say, wall, then the heat transfer is from the vertical surface, right? Let's say from inside to outside. When you will study the roof, then the heat transfer is from the horizontal surface, right? From outside to inside or from inside to outside. Or sometimes you may come across some slope as well, because some of the roof, they are mounted like this in this shape, right? They are mounted, I mean, they are constructed in this shape as well. So in that case, I mean, inside of the air will be calculated from at certain angle, let's say 45-degree angle. So depending upon the whether that's a still air, I mean, normally we take inside air as a still air, whereas outside air, it has certain velocity. So let's say if the velocity is, let's say, 15 miles per hour, that's very high velocity, or normal velocity, which is 7.5 miles per hour, or it is SI unit is also provided 6.7 meter per second or 3.4 meter per second. Normally, this velocity normally we take during the winter weather, whereas the 3.4 is normally taken during the summer weather. So this way, by using this table 5.2, you can directly calculate the value of the resistance because of the, I mean, outside or inside, because of the convection. That convection could be inside the room and that could be outside of the wall or outside of the roof, right? Similarly, there is a concept of the effective emittance, right? Effective emittance basically is the emittance because of the two surfaces, right? That give you the equivalent emittance because of the two resistance. Because the two surface, let's say one surface and two surface, if it has T1, then it has certain radiation. Any of the surfaces that has a certain temperature, it has radiation. If the human body has a certain temperature, it will emit radiation, right? So let's say emissivity of the surface 1 is epsilon 1 and the emissivity of the surface 2 is, let's say, epsilon 2. So the effect of both we call the effective emittance, and this is effective resistance is a function of the orientation, heat flow, air temperature, right? So as you can see from table 5.2, you can calculate the value of the effective resistance, right? You can calculate the value of the effective resistance for various surfaces. I mean, the surfaces could be the metallic one, as you can see, different. Normally, the emission rate of the metals is relatively high. As you can see, in some case, it has the 0.7 in the glass as well. Let's say regular glasses 0.74, right? Uh, this is taken from the ASHRAE Handbook Fundamentals. Right. Similarly, we have the thermal resistance because of the thickness of the airspace, right? As I mentioned that in the previous slide, if we know the thickness of the airspace, we can have the thermal resistance. So this table, the table 5.3a, it provides the thermal resistance of plane airspaces. As you can see, I mean, this is the thermal resistance, right? If the airspace thickness is 0.5 inch and if the airspace resistance is 0.75 inch, whereas the resistance because of the airspace, it depends on the effective emittance, right? For different value of the effective emittance, right? What is different value of the effective emittance, as well as the mean temperature, right? Mean temperature, what is the temperature difference? As I showed you here, I mean, the resistance because of the space, right? Let's say I show you in the previous slide, this is the airspace resistance. So this is not so simple to calculate the airspace resistance. This is a function of a different parameter. For example, the what is the air temperature, right? What is the effective emittance and the thickness of the airspace. So from this table, you need to know the thickness of the airspace, the airspace mean temperature and the temperature difference between the two surfaces, right? And what is its orientation? It is a heat transfer direction is horizontal at certain 45-degree or in the vertical direction. So accordingly, you will calculate the thermal resistance in the airspace, right? And then in heat transfer in building structure, there is a very important concept. It's called thermal bridge, right? Uh, Thermal bridge is basically an area, right? An area or a component of an object which has a higher thermal conductivity than the surrounding materials, right? So it creates a path of least resistance of heat transfer. So that's why we called it as a thermal bridge. So let's say if we have a river, let's say this is a river, right? So let's say this is a river. So what is the function of a bridge? So bridge will basically connect this one bank of the river with the another bank, right? So it will allow the people to move. So similarly, when we say the thermal bridge, so thermal bridge basically it is an area where the thermal resistance, right, where the heat transfer resistance is minimum. So that means if the heat transfer resistance is minimum, so that means the heat will flow. I mean, the heat transfer will be much larger compared to the other component. So that's why it is called a thermal bridge. But the thermal bridge is not good for the heat transfer in building structure. For example, if you look at this figure, basically this is the floor and this is the wall, right? So even inside of the wall, there is an insulation. It makes sure that the no heat flow from inside of the room to down to the ground. I mean, from floor to the down. Similarly, in the foundation wall, there is an insulation. It makes sure that the no heat flow from here to here because there is an insulation. But even then, because of this thermal bridge, as you can see, this is basically the thermal bridge. I mean, the structure has created a thermal bridge. I mean, if you look again, so as you can see, I mean, let's say this is a floor and this is a wall. So that means the heat transfer here is much larger. The heat transfer is much larger. So that means from inside, I mean, you cannot put the insulation throughout the floor. Similarly, you cannot put the insulation. So, I mean, there is a path where the heat transfer will be much higher. So that means you need to stop that path. You need to break that connection. As you can see even here, I mean, in that figure, let's say the interior is much warmer. The temperature is, let's say, 70 degree Fahrenheit, whereas the outside is, let's say, 34 Fahrenheit. That's the exterior. So exterior is much colder and interior is much warmer. So that means although there is an insulation outside, right? Because of this insulation, I mean, no heat can flow from outside to inside, or the cold air cannot come through this one. But because of the construction of the building, as you can see, so this act as a bridge, thermal bridge. So what happens from the inside of the room through conduction and convection, the heat comes in this component, and then through the conduction it goes outside. So there is a loss of the energy, right? So that's the role of the thermal bridge, that you need to break that. You need to break that connection. And how can you break that connection? I mean, to overcome the effect of the thermal bridging, I mean, following suggestions are presented. One of the suggestion is to use of the low thermal conductivity bridging material. So it is recommended that for bridging, you should adopt a material which has a low thermal conductivity, or you change the geometry or the construction of the system. And lastly, you can put an insulation shed around the bridge. As you can see here, I mean, If you allow this, I mean, from inside the heat will flow. I mean, the heat will flow and then it will goes there. But if you put here some insulation material, that's called the thermal break, then the heat will not move from inside to outside. Normally in building, when you are building, I mean, constructing different flats or the building, normally what they do, they put some space between one part to another part, and that space, air space, they act as and a break for the thermal bridge. The overall heat transfer coefficient in the walls and roof, they are calculated by assuming that the heat transfer is a steady state. Steady state mean the temperature at one location remains the same. I mean, let's say this is our house. Steady state mean whatever is the temperature inside, let's say what right, and whatever is the temperature outside, it is not changing with respective to time, right? But it may change from location. Let's say from inside location is different, so it is different temperature. Outside is different temperature. But this temperature will not change with respective to time. Similarly, this temperature will not change with respect to time. And will use an ideal construction method. Similarly, the other assumption is the surrounding surfaces are at ambient temperature and the variation of the thermal conductivity with temperature is negligible. In other words, we will use the constant value of thermal conductivity, because for the application of air conditioning, normally we use the building structure. We are studying building structure, I mean, with reference to the heating or with reference to the cooling. So for this particular range of the temperature, the value of the thermal conductivity is not changing so much. So we can assume the value of the thermal conductivity to be constant. So these are the assumption on the basis of which we can calculate the overall heat transfer coefficient by using the method that I have described previously, by using the equivalent resistance, and from equivalent resistance we can calculate the overall heat transfer coefficient, because resistance is the reciprocal of the conductance, or in other words, conductance is basically 1 by UA, right? So if you know any of this, whether you know C or whether you know R, so each of the component can be calculated. So let me give you a few examples. Let's say for the wall. So this is a wall. This is a typical wall. I know that this type of wall is not constructed in our area, but in extreme cold areas, especially in Scandinavian countries, such of the wall is very famous. As you can see, I mean, outside we have the air and then we have the brick. You can read from this one, let's say the outside surface. This is surface 1, right? That consists of 15 miles per hour wind, and then this surface is a brick and the thickness is, let's say, 4 inch. And then we have inside and the third layer as well, that's a cement mortar. And then I mean, a mortar mean by which we have joined the other surface. This is a cement layer, and then we have the block. This is a concrete block, I think. Yeah, this is a concrete block. And then we have the reflective air space. So let's say this is a reflective air space as well. Then another layer, let's say this layer is made up of the vertical furring, and then inside we have the gypsum wallboard. Normally they use the wallboard inside of the room, and then we have the inside air, right? So these are when we analyze the wall. So as you can see, there are so many resistances. One of the resistance outside resistance will be convection, right? So for this one, what we need to calculate the resistance of the convection, we need this velocity of the air. I mean, what is the velocity of the air, whether it is a 15 miles per hour or the 7.5 miles per hour. So accordingly, we can have accordingly we can have the resistance outside, or if we know the value of the convective heat transfer coefficient outside, right, then by using 1 by HO AO, we can calculate the value of the thermal resistance. And then for brick material, as I showed you, different construction material have different value of the resistance because of the conduction. I mean, you can use again for the brick you can use two method. One method is the calculation method. I mean, you use that formula delta X, right? Sorry, that method is L, right, divided by K, sorry, delta X divided by KA, KAL, right? So if you know that what is the length of the wall, thermal conductivity, or the thickness of the wall, you can calculate the resistance because of that brick, right? Or this is the first method. Second method is, I mean, ASHRAE has provided different values of the resistance, right? So depending upon the material. So for brick, they have presented that what is the value because of the brick. If you know the thickness of that brick, you can calculate the value of the resistance. So you can you can save the computation time. Similarly, let's say inside is the concrete block. So again, for the concrete block, we have, I mean, the values of the thermal resistances, a range of the thermal resistance that are provided depending upon what is the thickness of the block, right? What is the thickness of the block? Or other way is the computation of the resistance of that block. I mean, if you calculate the thermal resistance of the block by computation method, then what you have to do, I mean, first of all, you have to divide with the layer. I mean, there are three parallel resistances, right? These three parallel resistance, they are because of the air gap. And similarly, these three parallel resistances, they are in series with, let's say, this thickness and this thickness. So the simplest way is, I mean, by using the thickness and the nature of the concrete block, you can have the thermal resistance. And then similarly for the other layer, I mean, you can adopt the same procedure to calculate the value of the thermal resistance, and then you can add up because all of the resistances, they are in series, and you can get the R equivalent, right? Just like in this case, that each of, I mean, from the previous tables that I showed you, from those tables, you can have the values of the resistance. For example, let me show you. For example, if the speed is 15 miles per hour, and you can have the resistance, let's say 0. That resistance is 0.17, and we can see in the previous table, I think that was in, let me show, I think maybe not this one, maybe in this way. If we have, the speed was how much? 15 miles per hour. So where is 15 miles per hour? So this is the wind is 15 miles per hour. So we have to read the values of the resistance. So this is the resistance. So let me see. This is the value of the 0.17, right? So let's say the resistance here will be 0.17. So let's say, yeah, 0.17. So similarly, if you know the types of the material and what is its thickness, you can read the value of these resistance. Similarly, for the other material, you have a detailed value of the thermal resistance for different materials. So finally, you can add up. I mean, if you add up these materials, you can have the equivalent resistance. And when you have the equivalent resistance, you can have the overall heat transfer coefficient, because overall heat transfer coefficient is the reciprocal of the R equivalent. And similarly, just like the procedure we use for the wall, we can also calculate we can use the series resistance procedure to calculate the overall or the equivalent resistance for the roof as well. So you can see a roof could have a different component, right? For example, you know that, I mean, the lowest, this is let's say this is the inside of the room, and then from inside the first layer is normally, I think, the false ceiling. This is the ceiling, and then this is the holder of the ceiling, and then we have the concrete, and then we have the finished concrete. So you can see there are different layers of the roof. For example, this is the outside surface. So this is the outside surface. So if we know the how much is the velocity of the air, we know that from the velocity of the air we can have the resistance. Similarly, the next one is the finished, the concrete, and then we have the concrete block, and this is the holder of the ceiling, right? And then we have the false ceiling. So each of the material, and then the inside air. So each of the material, they have different thermal resistance. So overall resistance will be the sum of all the resistance. And from the equivalent resistance, we can calculate the overall heat transfer coefficient. And then from overall heat transfer coefficient, we know that the value is UA delta T. So we can calculate finally the heat transfer between the 2 points, let's say from inside to outside. Let's say another example. For example, it says that compute the overall heat transfer coefficient. So what is the value of the overall heat transfer coefficient U for the roof ceiling combination? So that means we have a roof. This is the roof, and then we have a ceiling. So there is a space between the roof and the ceiling, right, as shown in figure. And this is a wall. The wall assembly is similar to table 5-4A. So I showed you just, I mean, in previous case, this is the 4-A. So this is wall is similar to this one. I mean, this wall is similar to table 5-4A with an overall heat transfer coefficient. So basically the conductance for the wall is given, right? Similar, the roof assembly is similar to 5-4B. So roof is same as I showed you in the previous slide without ceiling, and has a conductance of, so again conductance is given between the air space and the outdoor air, right? So the conductance value is given between the air space and the outdoor air. And then this is the air space, right? The ceiling has a conductance of, so the value of the for the ceiling, this is the ceiling, the conductance is given, right? The airspace is 2 feet thick, so the thickness of the airspace is also given. So there is no problem to calculate. Even the value of the conductance is already given, right? The ceiling has an area of this much, so the area of the ceiling is also given, right? And the perimeter is also given, right? So perimeter is also given, so this height is also given. Let's say this height is also given, right, which is 2 feet. So what you need to know, you have to calculate the overall heat transfer coefficient. So can anyone tell me that what will be the resistance combination in that case? How the resistance will be formed? How the resistance will be formed in that case? Anyone? Any idea what will be the, I mean, how the resistance will be created for this case? What about the wall and the roof?
Hello, Assalamualaikum, sir.
Yes.
Sir, I think the wall will be in parallel to the roof, and the roof and airspace and ceiling are in series together.
Yes, that's right. This is very obvious, right? So we can calculate the equivalent resistance. I mean, as you can see in that solution, that first of all we have to calculate the overall resistance between the roof and the wall. Right? So that's between the roof and the wall. So you can sum up because those are parallel with each other, and we know the conductance and resistance, they are, I mean, reciprocal of each other, right? So the equivalent is conductance between the roof and the wall. I mean, between the roof and the wall, because they are parallel with each other, and this is the reciprocal of this. So this will be the sum of that. Whatever is the conductance of the wall plus the conductance of the roof. And then what will be the thermal resistance? That will be reciprocal of that. So the thermal resistance between the roof and the wall, that will be 1 by this value, right? And this value is basically the sum of that. So this is the equivalent resistance between the roof and the wall. And then the roof and wall, they both are in series with the ceiling. right? So you can add up that. So this is 1 by Cc into AC, right? And finally, you can put the values because all of the values are given. This value is given in the statement, this value is given. So you put up that value so you can get the R equivalent. Whereas the overall heat transfer coefficient is a reciprocal of this, right? So similarly, we can have the, I mean, instead of calculating this component, I mean, you calculated the 3 component and you add up that, and then finally you calculated the overall heat transfer coefficient. The problem is even simplified by the ASHRAE. I mean, you can directly calculate the overall heat transfer coefficient of the various component. As you can see in this figure, for example, the overall heat transfer coefficient of various fenestration product. Fenestration mean, I mean, the window, right? And the window consists of, it can, the single glazing, I mean, only single glass sheet is used. For example, this is the single one. In some case, the outer has a glass, then inside again has a glass. I mean, there is a um, uh, air air spacing between them, right? And similarly, that called the double glazing, right? And the value could be different, their thickness could be different. As you can see in that table, let's say if there is a single glazing and the thickness is, let's say, 1 by inch of the glass, then you can read the value of the U overall U factor, but at a different condition. For example, for the frame, because the window consists of various components. For example, for the frame, right, and similarly for the aluminium without thermal break, right, aluminium with thermal break, or the reinforced, or the aluminium cladding wood, right, or the insulated fiberglass, right, or the fixed one, I mean the insulated fiberglass. So for different types of the windows, you can have the thermal overall heat transfer coefficient, because you know that there are various types of the fenestration. Some of the window, I mean, let's say the single glass window, they are mounted with, let's say, using the aluminium one, right? Normally they are sliding one, right? Some they are based on the wooden one, right? Some they are, I mean, they can have different variety. So depending upon the variety of that single glaze window, the value of the overall heat transfer coefficient will be different. And again, it depends on the thickness of the glass sheet. So you can see for the different, let's say if there is a double glazing, then in case of double glazing, the air space will matter now. Let's say this is a double glazing and this is the spacing between the double glazing. So accordingly, and what is the types of the fixture, accordingly it will have an overall heat transfer coefficient, right? So similarly for the other one, right? Again, you can see depending, I mean, this is the value of the overall heat transfer coefficient for various wind speed, right? I mean, wind speed mean this is in miles per hour, this is in kilometer per hour. So let's say this is miles per hour in kilometer per hour. So if the, for different wind speed, the value of the overall heat transfer coefficient is different. Right. Similarly, this is the overall heat transfer coefficient for wood and steel doors, because the door is also mounted inside a building. So there are chances that the heat can flow even from through the wooden or the steel doors. So it depending upon which types of the door you have installed. For example, this value of the overall heat transfer coefficient is for the wooden door. Similarly, this is for the steel door. Depending upon the thickness of that door and which type of and using the description, for example, up to here the thickness is the same, but the description is different. I mean, let's say panel door with this much inch of the panels, or the solid core flush door. So the, according to the nature of the door, the value of the overall heat transfer coefficient is different. You can select that from this table. I mean, in addition to that table, ASHRAE has a detailed list of the values for overall heat transfer coefficient. And similarly, from this table, you can calculate the heat loss through, I mean, below the basement wall, because I explained you that even a floor has different layer. For example, let's say if this is the first floor, I mean, where you have tiling, right? Whereas a wall goes down, I mean, the side walls goes down. I mean, below than that, we have the foundation. We have the foundation, but this floor has many layer. I mean, maybe the top one is the tiling, right? We call the finished grade, and then we have the concrete, right? And in between concrete, you put some cement layer to join the tile with the concrete, and then you can have the grading, right? And then you can have the soil, right? So accordingly you can calculate the, even sometimes they put insulation layer as well. I mean, here they put the insulation layer as well, right? So depending upon the nature of the basement wall, you can calculate how deep it is. I mean, how deep it is. Accordingly you can calculate the value of the heat loss. This is the heat loss, right? A heat loss coefficient, right? Heat transfer coefficient. I mean, what is the heat loss? I mean, value of the U because of this basement, depending upon the thickness, how deep it is. For example, here the values of the depth is given starting from, let's say, 1 feet to 7 feet, or in meter, right? You can have the value of the R. As you can see, different value of the R. Similarly, for the heat loss through the basement floor, you can calculate depending upon the thickness, right? And how to calculate the heat transfer from the soil or from the ground, right? There is a formula for that. The heat transfer from the ground is equal to UA. T, I mean inside temperature of the room. TG is the ground temperature. But the ground temperature is not constant. It varies from location to location. So how we calculate the TG, right? TG is basically the difference of the average temperature. I mean, annual average temperature. For example, GIK has an average annual temperature. Let's say, I mean, first there are different types of the average. There could be the average based on day. That's called the daily average, right? There could be the average based on the month. That is called the monthly average. Similarly, there is an average temperature we call the annual average temperature. So every location has three different average temperature. I mean, the average, daily average mean whatever is the minimum temperature of today and what is the maximum temperature of today. Let's say today is the 30th of December. So what is the minimum temperature? What is the maximum temperature? So T minimum plus T maximum plus T maximum, right, divided by 2. That will be the daily average. Similarly, based on the month, in a complete month, what is the maximum temperature? What is the minimum temperature divided by 2? So that will give you the value of the average monthly. Similarly, for the yearly, they use this one, or they also use the weighted average as well. Weighted average is method is slightly different than that. But anyhow, you don't need to go into that detail. So you need to know what is the average annual temperature for that particular location minus, this is called the lines of constant amplitude, right? That's called the amplitude of ground temperature. So this is again the location dependent. So we have the lines of this. This is called along that line the temperature remains constant. That's called the lines of constant amplitude of ground surface temperature variation. For example, let's say if your location lies on that, so the temperature, that's called the const AMP, the lines of the constant amplitude, right? So you need to know that what is your average temperature for that particular location and what is the value of AMP, and then you can calculate the ground temperature. So by using the ground temperature, you can calculate the value of the heat transfer coefficient, I mean value of the heat transfer because of the ground. So these are, for example, this is an example of the annual average temperature. in different cities of USA. For example, one of them, let's take the famous one. Let's say New York has an average winter temperature of, let's say, 1.8 degrees C. So using that average temperature, T average, and the AMP for that location, we can calculate that what is the ground temperature, TG. And then from ground temperature, we know that what is the inside temperature, we can calculate by using the UA, and then we can have the what is the value of the heat transfer through the soil or through the ground. And then there are possibility that the heat may flow through the slabs, right? This is a slab, or the we also called it as a concrete. So the heat transfer through the concrete, uh, it depends on the I mean, this is stop by using an insulation, right? This is an insulation. So it depends upon what is the depth of the insulation. So it depends on the value of the D. As you can see, here the D value is 0. So that means there is no insulation here. So when there is no insulation, then the value of the heat loss is much higher. As you can see, the value of the heat loss is much higher. So if you increase the value of the D, let's say 1 feet, and then 2 feet, and then the 3 feet, then the value of the heat loss coefficient is much less. It depends on the value of the insulation. So if you know, let's say you have used certain types of the insulation, let's say if you have used this insulation and you know the depth of that, let's say the depth is 3 meter, then by using this one and the depth is 3 feet, then you can calculate the value of the U because of that slab. So that you can calculate the value of the heat loss coefficient. So once you know the value of the heat loss coefficient, and this is the perimeter of the slab, so finally you can calculate the value of the heat transfer because of that slab. Right. So lastly, there could be the buried pipes below the surface. So let's say if the steam is flowing that through that pipe, so there is a possibility that the heat can flow from the pipe to inside of the room. So how to calculate the value of the heat transfer because of that buried pipe? So what you need to know, first of all, you need to calculate the resistance because of this one. So let's say if this is Tg is the surface temperature of the soil, and this is I mean ground, this is the temperature of the ground, and this is the temperature of the surface of the pipe. Let's say D is the diameter of the pipe, and this is the height from the center of the pipe to the surface. Let's say that's value Z, and L is the length of the pipe. Then the resistance because of this can be calculated with the help of this one. So this is the resistance between the ground and the pipe. As you can see, this is the function of ln 2L by D into 1 minus ln L by 2 Z divided by ln 2L by D over 2 pi KL. So L is the length of the pipe, D is the diameter of the pipe. So Z is that height between the surface and the center of the pipe, right? K is the thermal conductivity of the pipe, right? And then L is the length of the pipe, right? Sorry, K is the thermal conductivity of that soil, because heat transfer is through that soil. So this is the thermal conductivity of that soil. So by using this one,
excuse me, sir.
Yes.
Sir, sorry to cut you off, sir. This formula will give us the total resistance, the combined resistance of the pipe and the soil, or just the pipe?
So this is basically the heat transfer from pipe to that surface, right? So that means the resistance will be from pipe to that surface, right? So this is the overall heat transfer from the outside of the pipe, to the surface, to the soil surface, right? So that's the value of Rg. So that's why we are taking the surface temperature of the pipe, and similarly the ground temperature and the thermal conductivity of the soil. So once you know the resistance, then we can calculate the heat transfer, right? Because of this. So Tg is the temperature, this is the Tg, and Ts is the surface temperature of the pipe, and R is the thermal resistance between them, right? So that's the end of this chapter. Actually, I think this chapter should be very easy for you, because it covers most of the concept that you have already studied in heat transfer. Just the new concept is that if you have different component, how to calculate the equivalent resistance. So once you calculate the equivalent resistance, you can calculate the overall heat transfer coefficient. And once you have the overall heat transfer coefficient U, then the heat transfer because of that structure is very simple, UA delta T. Right? So I suggest you to practice these numerical problem. They are very similar to the concept that we discuss in our class. I mean, I think one of them is because of through a wall, one is through the roof, one is through the buried pipe, and one is, I think, through the slab. So one problem for each topic. You should practice this, right? If you have any question, you can ask me. Do you have any question?